So let's look at the function. Here's our function. And let's say I determine that between a and b, the function has a root r, or a solution. How do I determine that, knowing that the function is continuous? There is a theorem that we talked about a long time ago called intermediate value theorem that said that if I have a 1 unit, preferably a 1 unit interval, and a function is continuous and it changes sign from negative to positive, and it's continuous, that's mandatory, then the function must have a solution there, or a root, or an x-intercept. Okay? Perfect. Let's suppose I start somewhere. It's a algorithm, it's a step-by-step procedure. Bless you. Okay. So let's suppose I start somewhere. And let's suppose the starting point is B. I will denote B by x0, initial value, or initial starting value. Initial value. So that's my starting point right here. This is my x0. I draw a vertical line at this point. It crosses the function at point A, if you want. And here, I would draw the tangent, extending it till it crosses the x-axis. Can anyone give us the slope of this line? Too much thinking. Thank you. Thank you. F prime of x0. We agree?
Yep.
Perfect. Now, I am going to denote this point by x1, the x value, and I am going to call it the first iteration. Can anyone give us the coordinates of this point? Very good. Awesome. Can anyone give us the coordinates of this point? X0, comma.
F of y, or f of x, 0.
Awesome. Thank you. Very good. And now, I would like you to give me the slope of this line, and you can say you already have it.
You zoom out.
Zoom out. So I would like you to give me the slope of this line, of the tangent line, but you should say you already have it. Yes, I do. It's f prime of x0. But I want you to give it to me in a different way now, because we have 2 points. We have the point x0, comma f of x0, and we have the point x1, comma 0. So I want you to use, not the derivative, I want you to use algebra with this point and this point, which is x1, comma 0, and give me the slope of this line in a different way. F of x0 minus 0, awesome, over. Awesome. Okay, let's stop for a moment and go back and summarize what we did before we continue. Okay. Say it again. So f of x0 minus 0 over x0 minus x1. f of x0 minus 0 over x0 minus x1. This has to come from this. These two have to come from the same point. These two have to come from the same point. Perfect. So let's do this one more time before we proceed. Somehow I realize and I find an interval where this function has a 0 or a root. How? Knowing that the function is continuous and applying the intermediate value theorem, right? So I know that it changes sign on the interval a comma b. So I said, fine. I prefer a unit interval. We do. Then I say, okay, where do I start? The starting point is important and it's not always random. There are some conditions that I will talk about in a minute. But let's say, okay, I want to start here. I'm going to say that this is my starting point. Can I start closer? Yes, you can start anywhere you want. But don't start here or here. There's no point. Normally, the method converges, we say, in 3 or 4 or 5 steps at the most. But if you start too far, it will take longer. You will still get there. Yes?
So what does the first iteration mean?
Very good. I haven't explained that yet. I just named it. Yes. I just want to summarize what we did and then I'll explain. Good. So then you can decide to start at A. That's fine. I decide to start here at B. So I denoted my initial value x naught or x0. I draw a vertical line and I realized that this point has to have x0 as the x coordinate and y at that point, which is f of x0. Then I continue drawing a tangent at this point, whose slope I know must be f prime of x0. We know that for 2 chapters already. I will extend the line till it hits the x-axis. I denote this point by x1 comma 0. x1 being the first iteration, meaning this, before I continue. Would you agree that according to the graph and to the method also, x1 is a much better approximation of the actual root than my starting point x0? That's the first result, the first step towards finding R. So I started with x0, x1 will be a better approximation, x2 will be a better, and x3 will be a better. And I'll stop based on how many digits I want accuracy to be. So the first iteration, one more time, means a better approximation of the solution than the one I started with. So how did we continue? We had the slope of this line, but we can also determine the slope of the line using the 2 points we have. So y2 minus y1, which is 0, over x2 minus x1. Are you with me so far? Okay. Now, look at this equation and say, there are certain conditions, I'll come back. Look at this equation and I'm going to ask you, what do you think I'm going to solve for? Of course, because x1 will be a better approximation of the solution R that I don't have yet than the starting point. Clear? Okay, so let's solve for x1. What will you do? We shouldn't be thinking. You should only do this and then say, I know. Thank you. So f of x0 equals f prime of x0 times x0 minus x1. It's a proportion. I cross-multiplied. Awesome. Now I will distribute. Remember, what is the variable now? I have this, and I have this. I started it with it. So I know exactly what it is. And I know this, and I know that. So what is the variable then? Of course, x1 is the key. So I'll distribute. So f of x0 equals x0 times f prime of x0 minus x1 times f prime of x0. I prefer to move this here and this here. So x1 f prime of x0 equals x0 f prime of x0 minus f of x0. Finally, I have x1. What do I do to get to x1? Both sides by? Good. So this is x0 minus f of x0 over f prime of x0. Stay with me. This is not done. Is it clear so far? Yes? Caesar, go ahead. Okay, I love it when you answer your own questions. Okay, so let's come back. So I found in my first step, my first iteration, I found a better approximation of the solution. What do you think I'm going to do next? I'm going to draw a vertical line. It will hit the graph in this point, and I'm going to draw a tangent. I'm going to extend the tangent. It will hit the graph. I can no longer show. It would hit the graph, and this will become what? Do you agree that x2 must be a better approximation of r than x1 was? Good. So now, with no calculations, I would like you to give me x2. The calculations are the same. The slope with 2 points. I'm ready. Perfect. This is Newton's method. N plus first iteration in general, what will that be? That's it. You can continue forever, as many times as you want, and you will get the best approximation you want. With 2, 3, 4, 5, 10, 1100 digits, whatever you want. Any equation that no one can solve algebraically. Okay, there are two things here that we have to mention. You cannot choose an x0 or x naught. Look at this expression and say, I know. I cannot choose an x0 that does this. That does what? When f prime is 0 at that x0. So I cannot choose an x0 just simply because I want to if f prime is undefined at that x0. Because I will not be able to pass the first step. So that is one key, one requirement. You have to make sure that the x0 you start the method with does not make f prime 0. Because as you see, f prime is in the denominator. So that's the first condition. You have to be very careful here. Choose x0 such that f prime of x0 is not 0. Otherwise, you're in trouble from the very beginning.
X0 is going to be the point you choose first, correct?
X0 is the first value you start with. If the derivative at that point is 0, you can't pass anything. You can't determine anything. Okay, second condition. Here's what happens, which will basically not really happen. You can look at the graph, right, also. But if you want to determine this solution, and somehow this happens, there is a bump or a max or a min or a turn, and you start here, the method will never converge. Because you will always get in this area, you will never get here, because there is a max or min between your x0 and your r. You have to be very careful. If you choose x0 in such a way that there is a max or min between your x0 and the actual solution that you are trying to find, the method will never converge. You will never get there. You will never find r. So make sure this will basically, it's very rare that it will happen because you're going to look at the graph, right? You're going to look at the graph and you're going to find 2 points within a 1 unit interval, although it can happen, but it's very rare. But this is the second condition. So no max min between x0 and r. If you choose x0 in such a way that there is a max or a min between x0 and r, we're in trouble. The method will not converge.
So you would get a root, just not the one you're looking for.
Well, you can have this like this, and you start here, and the method will never converge. It doesn't have to have another root. I confused you with that. Sorry about that. Let me give you another example. So this is the what you're interested in, and you start here. The method will never converge because there is a max or a min, or in this case both. You will always stop here, and all the method will happen here, will never get to the root r. Okay, so let's look at any equation. You can create any equation that you can think of, anything. So if you like to choose, you can choose. They are on page, or you can make one up with anything, natural log and trig functions, and you name it, whatever you want. On page 342. You didn't expect that, did you? On page 342.
What numbers?
From
24.
17 through 22 for now.
19.
Or 17 through 17 basically through 28.
19.
19. Okay, perfect. 19, we have x minus 2 squared equals natural log. One more time. Yes, 342. Right? X minus 2 squared equals natural log x. Perfect. I hope you agree that no one can solve this algebraically. There is absolutely no method. There's nothing we can do here. Okay, so first step is x minus 2 squared minus natural log x equals 0. It's very clear that we have to create the function. Then, and we're trying to find its x-intercept or root. So f of x will be x minus 2 squared minus natural log x. Is this function continuous?
Yeah.
Yes, there's a difference of two continuous functions. However, remember, the domain of this function is 0 to infinity, and they have to have common domain. So now the domain of the function is 0 to infinity. Even if this one has all real numbers, but this one does not, I can't pick anything to the left of 0. The function will not exist. Okay, so since it's continuous, so number one, f continuous on 0 to infinity as a difference of two continuous functions. Now, I have to plug it in the calculator because I have to find an interval. And I have to look for a 1 unit interval using the intermediate value theorem. So let's put in the function in y equals. So x minus 2 squared, parentheses, x minus 2 squared, and then minus natural log x, close the parentheses. So we go to second and table, and I'm going to try 1, and then 2. Good enough. I don't have to determine all solutions. I know, and just remember that when you start working on this, I only want one solution. Obviously, if you know how to solve or find one solution, you'll find the other ones. So for any problem, I just want one solution. So I found an interval between 1 and 2. At 1 is positive, at 2 is negative. A continuous function has to have a 0 between 1 and 2. So I'm going to write f of 1 positive, f of 2 negative. Therefore, there exists C or R in this case, it doesn't matter, in the open interval 1, 2, such that f of R is 0 by IVT. When we talked about IVT, then I said it does not give us the solution, but it guarantees that there is a solution between such and such. So now, in step 3, we are going to apply Newton's method. We have to decide what is our x0. So let's find f prime first. So f prime will be 2 times x minus 2 times the inner function prime, which is 1, minus 1 over x. So obviously it doesn't matter if I want to start with 1, the function derivative exists at 1, or 2, the derivative exists at 2. So there is no danger here. We can start anywhere you want. So in step 4, we have to choose x0. Okay, fine, we want to start with 1. So now we will create a function that is Newton's method. I'm going to call it g of x. In step 5, we create a function called g of x, which is Newton's method. You can call it the way you like, it doesn't matter. You don't have to give it a name at all. So it's x minus, at the top, I copy f of x, and at the bottom, I copy f prime.
Why is it x minus?
That's Newton's method.
Oh,
So x that we pick
Yeah.
minus f of x over f prime of x. What do you think I'm going to plug in first?
1.
Right. What do you think I'm going to plug in second? 2. Whatever the result is of the first iteration. Because the next step depends on the previous step. Right? So let's put this function in. Newton's method. In y equals, insert an x, subtract, parentheses for the top, this is the function, all the way, close the parenthesis, and divide by parentheses. Do I have enough parentheses? Yes. 2, parentheses x minus 2, close the parenthesis, minus 1 divided by x, and close the parenthesis.
Should you put parentheses around 1 minus x? Or 1 divided by x?
No, because it's like 1/2. I don't need to.
You won't need a parenthesis after the first subtraction to keep the whole fraction together. Separate from the x.
No, because I can write x minus top divided by bottom. I do have parentheses around the top. I have this right parenthesis around the top.
I just meant like encompassing the whole fraction.
The whole
aside from
fraction, you
x.
want to put outside parentheses one more time. There is no need. Yes, you can, but there is no need because the top divided by the denominator, if something else follows, you're right. If I have minus 1 or something, but no, there is no need. I think I understand what you're saying. So I do have parentheses here mandatory, and I do have parentheses here mandatory, but you wanted to put another parenthesis like this. There is no need
Okay.
because it's a division. But it's not a mistake if you do. This is not a mistake. But there is no need for that. Is
Would
that
it be okay to put the parentheses around 1 over x?
you can.
Okay.
If you want to put parentheses here, yes, but because it's 1 over x, you don't need to, but that's fine. That's no mistake. Yes. Good. So now we go to second and quit. And now I want to call function y1, right? We use the y1, yes. So I want to call y1. No, I want to go to functions. No. I want to go to functions, y variables. Yes, here it is. Okay, I call function y1.
What was that?
Okay, let's do that again.
Second variable.
Let's do that from the beginning. So variables, and go to y variables.
Oh, so that's, you want
Click.
variables.
Yes,
Oh.
yes. Click on a function and call function y1. What do I plug in y1 again?
1.
Thank you very much. So I started with 1, and the first iteration, which is x1, and I will copy it down. We have not decided how many digits accuracy we want. 5, 6, 8. It's up to you. How many digits? We want 5. Okay, 5 digits. Accuracy. Perfect. So then I have to copy 6. So 1.3333333. Here's what we do next.
That's x1.
That's x1. Now, careful what we do next. Please pay attention 1 second. Second, and the previous entry. This time we go over 1, and we recall the previous answer. We want now to plug in the Newton's method, which number?
1.333.
Correct. Awesome. And press enter.
That's
And
the second.
That's the second one.
And then do it
So
again
this
for a
is
third time.
exactly 1.408579. X2. So this time, all I have to do is just copy the previous entry. I don't have to do anything else because you will put inside the previous answer anyway. Press enter. So this is X3, which is 1.412381. I copy second and entry. I don't have to do anything, just press enter. Is this good enough? No, it's not. It doesn't really repeat the previous 5. So I have X4, which is 1.412391. Maybe this is enough, but I have to see the next one. Yes, it's enough. So we solved an equation that no one can solve. Yes, it's 1.41239. This is what we wanted because we decided 5 digits. 1, 2, 3, 4, 5 digits. Once they repeat, I stop at the previous iteration. And of course, you can go on forever. Now, is there another way of determining the solution with the graphing calculator? Yes, there is. But you have to graph it. I'm sorry, I have to go back. Sorry. This is the Newton's method. Don't even look. I have to go back and graph the function and find its 0. But I will not have any number of digits accuracy because the calculator will stop somewhere. So it will run out of space. So this is Newton's method. And now you know how to solve any equation on the planet. Okay, so I know we have about 12 minutes. So what would you like to do in 12 minutes? Other than eat some candy, please. I brought it for you. Say it again.
Make like geese. He wants to leave.
So you'd like another Newton's method?
Yeah.
Would you like another graph? Or would you like an optimization? Newton's method, you loved it. Okay, good. So would you like to make an equation up? Or would you like us to come up with an equation?
Come up with one.
Would you like to look at something with sine x?
No.
Yeah. So do
No, no sine x?
Yeah, sure.
Okay, what about
Yes, I know.
3 sine x equals x? 3 sine x equals x. So, I didn't know you were shy. Did I have to tell you several times to everyone? I'm talking to everyone. I buy them, I carry them, and you just leave them here. Well, I'll take the rest tomorrow to my other classes.
No, bring it back Monday.
I'll bring it back on Monday.
I came in late, so I didn't want to stand there and interrupt.
Okay. So first step towards finding solutions. First of all, let's decide how many digits. 6 digits. So we look at the function first, which is 3 sine x minus x, because it's 3 sine x minus x equals 0. You understand that no one can solve this equation algebraically. Is that clear?
There's one you made up.
Oh, I copied it from the book on page 342,
That's not made up.
problem 16.
Oh, okay. Somebody made that.
Good. So is this function continuous everywhere? On negative infinity to infinity. Number 2, let's plug it in. And find an interval. Sine x minus x.
That was 3 sine x.
It was 3. Okay, very good. Good. So I already see something here happens at 0, right? But I don't want to start with something that I already have. It's a solution. When x is 0, y is 0. No problem there. So let's go back to make sure that the mode is in radians. Make sure your mode is in radians. So second in table, I'm going to plug in -1, and then 0, and then 1, and then let's say -2. Good. So I found a solution between what? Between 1 and -2. Okay, fine. Although it's a huge, I don't want to use 0 because I can't start at 0. 0 is a solution already. Yes. I'm sorry. Yes, you can plug in 2 if you want. So you can say, but you don't have the change of signs between 1 and 2.
You do between 2 and 3.
Okay, let's look at 3. Good, that's good. So the interval is 2, 3. Perfect. So f prime equals 3 cosine x minus 1. There is no danger. You can start at 2 radians or 3 radians. The derivative will not be 0. We have to create the function that we plug in, x minus 3 sine x minus x over 3 cosine x minus 1. Which one do you like it to be x0? 2. Okay, fine. So let's go to y equals. Make sure you plug in, insert there x, and then minus, and then parentheses for the top, and we already have the top. Divide by, in parentheses, 3 cosine x minus 1. Ready? So we go to second and quit.
Varies.
I can recall what I have, replacing the answer by whatever you said. You said 2? Okay, 2 it is. So y1 evaluated at 2. Negative 1.6173. Something is potentially wrong because
It's not like it.
we'll see. We'll see in a minute. We'll know if it doesn't converge, and that doesn't get closer and closer to a solution between 2 and 3, then we know something, we messed up something somewhere. Okay? So I will say for now that x0 is 2, and then x1 is negative 1.617396. We want 6 digits, so I'm going to copy 7.
That should get me.
You got something else?
Uh-huh.
Okay, let me look. That's what I said. Something is potential. Oh, I forgot the parenthesis. Thank you. That's what I said. Something that is not, it's a little bit fishy. I said that. Okay. Yeah, I forgot to put the parenthesis right here. And the calculator did whatever else. Thank you.
Yeah, that makes sense.
Good. So then I go to do that again. Yes, now it makes sense. Much better. Thank you. So then x1 is indeed 2.323732. 2, 4, okay, and 0, 6.
Yeah, I mean, the result should be close to
Right,
x0, right?
right. That's what I said. Well, sometimes it can jump around a little bit at the beginning, but it has to converge quickly. But it can jump around a little bit. Okay, so then I want this, and I replace the 2 with the previous answer and close the parenthesis. 2.279594. That's my x2. 2.2795948. And then I copy, and I get 2.27. This is x3. 2.27886286. And then maybe one more time. 2.278862. When we wanted 6 digits and we stop, the previous one is good enough.
Oh, you say 6 digits, you mean 6 digits from the 2 point, or?
From the point, decimal digits, yes.
Okay.
Yes. So that's good enough. I don't have to, since we chose 6 digits, since the next iteration repeats the first 6 digits, I don't have to copy anything anymore. So it converged in 3 steps. It can converge in more steps if we want more accuracy. But if we want to stop at 6, in 3 steps we found what we were looking for. Yes,
How do
Nico?
we figure out the x0 equals 2? Is that when it changed back to positive?
So I look for a 1 unit interval
Yeah,
in which the function changes sign.
yeah, by IVTs.
Yes. So at 2, it was
2.32.
yes, and at negative at 3, it was I no longer have that. I didn't write it down. So at 2,
2.35 or something.
okay, and at 3 was
At negative 2 was negative, and then 2 was positive.
we were looking at between 2 and 3. So in order to show that, I have to go back to the function. So I have to go back to y equals and clear everything. So I have 3 sine x. I didn't mean that. I meant this. X minus x. So here I plug in second in table.
Yeah.
I plug in 2, and then I plug in 3. So at 2 is positive 0.72,
Okay.
and at 3 is negative 2.
So we're figuring
So
out
this
what-
is not in, you're not plugging this in, you probably have the Newton's method in the table, in the function. Not in the Newton's method we plug it in, but in the function, original function,
So we're basically finding out the x interval, or x.
intercept, the
Okay.
solution of this equation. This is the solution of the equation. So in other words, if you want to check, you plug in x, what we just determined, 2.278862 radians, and this both sides will be the same with a minor error. of course. Any questions?